Here is the graph of the function y equals fx. Let's trace the graph from left to right. When we reach this point, the blue point, we cannot go up anymore. It means that this is some kind of a maximum. The same happens here. We cannot go up anymore. We can only go down. And here is another such point. Locally, from this point, it is impossible to go higher. And that's why all these points are local or relative maximum. Locally, they are the highest point, and they are relative maximum because if you cannot go up anymore, this is the highest point, but this is only relative for the surrounding. If you observe, this one, it's not only a local maximum. This is really the highest place on the curve. So it is also global or absolute maximum because it's the highest point compared to any other point on the graph. Here, we cannot go down anymore. So with those points, it is impossible to go lower. And that's why these points are local or relative minimum. What about absolute minimum? Observe the graph. The graph goes down forever. It means that this specific function does not have an absolute minimum on its domain. Definition: fc is an absolute or global maximum of the function f on an interval I if f of c is greater or equal to fx for all x in I. The magic definition is for the absolute or global minimum. fc is an absolute or global minimum of the function f on an interval I if f of c is less or equal to f of x for all x in I. We will write many times max max, and we also will say max for maximum and min for minimum. Example: let's find the absolute maximum and minimum of the function on the interval ab. And here's the function. Here's the interval a and b. We are just tracing the graph, and we see that you cannot reach more than this height. This occurs exactly where x equals 0, so the absolute max of this function on AB is f of 0. The absolute max is the value of the function, so it is f of 0 in this case. It is the height, it is a y value. And here, as you can see, it's the lowest that the graph of the function reach between a and b. So the absolute minimum is f of b. What about the same graph, but now I'm going to change a and b to be everywhere? This is the highest point. If the value of this point is c, then f of c is the absolute maximum of the function. And what about the absolute minimum? We already realized that on the domain of this function goes down forever, and that's why there is no absolute minimum. So you can see that there is a really big difference if we take the absolute max and min on the domain of the function or on a closed interval ab. Many functions have no absolute max or no min on their domains. Many others have neither absolute max or min on their domains. So you have all possibilities. Definition. fc is the relative or local maximum of the function f if f of c is greater or equal to f of x for all values of x in a small interval containing c, which means that on the little surrounding of x equals c, this is the highest point. And the matching definition is for the relative or local minimum of a function. It is if f of c is less or equals to f of x for any x in a small interval containing c. So again, this is very local. If I'm in the highest point locally to the surrounding, it is a local maximum. If this is the lowest point locally, which means I cannot go down anymore, it is a relative or local minimum. Example. Let's now find the relative and the local maximum and minimum of f. At this point, you cannot go up anymore, so it is a local max. And again, it is the value of the y. You can see why. fc is a relative and local maximum because look at the little surrounding of c. This is the highest point. And for the same reason, this is a relative minimum. Because if you take the surrounding of D, then this is the lowest point. So f of D is a relative or local minimum. If you look at this graph, by the way, this graph is neither absolute max nor absolute min, because on one side it goes down forever and on the other side it goes up forever. Look at the arrows. What is common to local extremes of a continuous function? For example, here we have 3 of those points. Here you can see that there is a horizontal tangent line, or the derivative of the function equals to 0. Here is the same thing. But also here. Here there's a sharp corner. It means that the function is not differentiable. It means that the derivative does not exist. So what is common to all those 3 points? I would like to recall that the c, which is in the domain of the function, and either f prime of c equals 0 or the derivative does not exist, we say that c is a critical number of f. It means that all local extreme values of a continuous function occur at critical points. Fermat's theorem. If f is a local extreme minimum or maximum at x equals c, and f is differentiable at x equals c, then the derivative of the function at x equals c equals 0. But then we have even a better theorem. If f is a local extreme minimum or maximum at x equals c, then c is a critical number of f. There are 2 kinds of critical numbers. If the function is differentiable, the only critical number is for which the derivative is 0. This is Fermat's theorem. But in general, you can also get an extreme when the function is not differentiable. Let's see one example, fx equals x to the power of 2. This is the graph as you know, and you can observe by looking at the graph that this is a local minimum. But x equals 0, it's also a critical point, because you can see, differentiate, we want this to be 0. So x equals 0 is the solution. So x equals 0 is a critical number of f, and the point 0, 0 is a critical point of the function. Be careful, the opposite of this theorem is not true. A function may have a critical number c and neither a local maximum or minimum at x equals c. An excellent example is the function x cubed. You would like to memorize this because x cubed is a really nice example for a few things, and one of them is this. I would like to recall that we already know that the critical number is x equals 0, and we should observe that there is neither a local minimum or local maximum at x equals 0. And again, if you forgot, we differentiate the function and it is 0 when x equals 0. So x equals 0 is a critical number of f, but there is neither a local max or min at x equals 0. Be careful. While the value of the absolute maximum is unique, it is the highest y value, it may occur at many values of x. The same is true for the absolute minimum. I can give you an example. What is the absolute minimum and maximum of the function f(x) equals sin x on the interval negative 2 pi to 2 pi? Let's observe the graph. Here's the interval negative 2 pi to 2 pi. And as you can see, absolute max, absolute mean, another absolute mean. But if you look, the absolute maximum is 1. It attains twice at x equals negative 3 pi over 2 and x equals pi over 2. The absolute minimum is unique, is negative 1, but it is attained twice at x equals negative pi over 2 and then x equals 3 pi over 2.